Hi, welcome back. We're in lecture 11 and the topic in this lecture is multiple regression. In the first segment I gave an overview. We talked about how to interpret coefficients in a multiple regression equation. Now we're going to talk about how those coefficients are estimated. And to understand that you need to know a little bit about matrix algebra. So I'm throwing in this segment for those of you who have no exposure to matrix algebra or if you feel like you need a little brush up. If you're really comfortable with matrix algebra, then you might want to go ahead and skip this segment and go on to segment 3. So this is a very skimpy but basic introduction to matrix algebra. We're just going to do some simple things, addition, subtraction, multiplication, and I'll point out some very special types of matrices along the way that hopefully you'll recognize and you'll see the connection between matrix algebra and statistics, particularly multiple regression. So first start out with the matrix. So a matrix is just a rectangular table of known or unknown numbers. It has a number of rows, a number of columns. The order of the matrix is always number of rows first, then number of columns. So this matrix that I'm showing you here, M, is a 4x2 matrix, 4 rows, 2 columns. But again, to reinforce that, it's rows, then columns. I always tell my students here at Princeton, the way to remember that is matrix algebra is really cool. Rows, columns, it's really cool. So rows, columns, it's a 4x2. So one common manipulation of a matrix in matrix algebra, and particularly when you're doing calculations for multiple regression, is to take the transpose of a matrix. And to transpose a matrix, you just change the rows and columns. So here, to take the transpose of M superscript T, all I did was just flip the matrix so that the rows are now the columns. So now instead of having a 4x2, I have a 2x4. Addition and subtraction in matrix algebra is really simple, and it doesn't take really knowing much more than just basic addition and subtraction. The only thing to know is that the only way you can add or subtract two matrices is they have to be the same size or the same order. So if I want to add, say, matrix M and N, they both need to be the same size. They both are 4x2 here. And then to add them, I just take each corresponding element and add them. So I go to row 1, column 1 in matrix M, row 1, column 1 in matrix N, add those, and I get my result. And I just do that for each cell in each matrix. That's real simple. Matrix multiplication is a little bit trickier, but again, not too difficult. The one thing to know and remember as we're going through these calculations is that two matrices can only be multiplied if they're what's called conformable. And what that means is the number of columns in the first matrix must be equal to the number of rows in the second matrix. That's what it means for two matrices to be conformable. This is the technical way it's written out for matrix multiplication. What we're going to do is take the transpose of matrix M and multiply it by matrix N. Remember, I can't multiply M and N because they're the same order. They're both 4x2. But if I take the transpose of M, then I have a 2x4 multiplied by a 4x2. Then that works. They're conformable. So let's see how this works. So I took the transpose of M. So M was a 4x2. Now it's a 2x4. And I'm going to multiply it by N. So I have a 2x4 matrix multiplied by a 4x2. So this is 2x4. I'm going to multiply that by a 4x2. What that will give me is a 2x2 product matrix. That's a 2 by 2. So number of rows in the first matrix and the number of columns in the second matrix. That's an easy way to start learning how to do matrix multiplication, is think about what's the product going to look like. So if I'm multiplying a 2 by 4 times a 4 by 2, then I know I'm going to wind up with a product matrix that's a 2 by 2. And this is the product out here. So the way I like to do this when I first started learning how to do this way back in grad school is think about the product matrix and how will I get row 1, column 1 of this matrix. Well, the way to get row 1, column 1 is to go across row 1 of the first matrix and down column 1 of the second matrix. So what I'm going to do is take the first element in row 1, that's the number 1, times the first element of column 1 in the second matrix. That's the number 2. So it's 1 times 2. And then I'm going to add the second element in the first row of the first matrix times the second element of the first column in the second matrix. So that's 5 times 4. So what I'm doing is 1 times 2 plus 5 times 4 plus 3 times 1 plus 4 times 3. So let's go through that again. That's 1 times 2 is 2 plus 5 times 4 is 20, so I'm up to 22, plus 3 times 1, so now I'm at 25, plus 4 times 3, that's 12, that gives me 37. So how did I get row 1, column 1 of the product matrix? I went across row 1 of the first matrix, down column 1 of the second matrix. I multiplied each corresponding element and took the sum of the products. And that got me 37. We could do that for row 2, column 1. So now I'm in row 2, column 1. So I take 2 times 2 is 4, plus 1 times 4 is 4, that's 8, plus 4 times 1 is 12, plus 2 times 3 gives me 18. Okay, that's how matrix multiplication works. Fortunately, R does this for us, right? But it's sort of essential to understand how it works so you can see how the regression coefficients are estimated when you're doing multiple regression, because this is what R is using as it estimates the regression coefficients. So in the next 10 slides, to illustrate addition, subtraction, multiplication, I'm going to go from a raw data matrix, you can think of this as like a data frame in R, to a correlation matrix, just in 10 slides. So here, let's look at a raw data frame. This is a matrix. Again, if you think about a data frame, it's a matrix, right? We talked about that in lab 1 for when we were first learning about how to manipulate objects in R. So we can think of this as having 10 rows. That's like having 10 subjects in a study measured on 3 variables. And you can imagine these are numbers on like a Likert scale of like 1 to 5 or 1 to 7. So we just have 10 people and 3 variables. The first thing I want to do is sum up those columns. And again, think about how you would do this just in regular algebra, forget matrix algebra. How would we calculate the correlation coefficient? Well, we did that way back in, I think, week 2 or 3, right? How did we calculate correlation coefficients? Well, we got the sums of squares, the sums of cross products, right? It's sum of cross products over sums of squares. How do you get sum of squares? Well, the first thing you do is you get the mean, then you get the deviation scores, then you square the deviation scores to get some squares. So that's exactly what we're going to do here. It's just we're doing it in matrix algebra, which sounds fancy, but it's the same thing. So the first step is sum all the scores in a column because I want to get means. So I sum all the scores, and that gives me this matrix. It's a 1 by 3 matrix, or it's just a vector, right? I got those sums because then I want to get means. So if I multiply that matrix of sums times 10 to the negative 1, that's the same as saying dividing by 10, but that's how we write this in matrix algebra, then I get the means. So now I have a matrix of means, or what I call here a row vector of means. Now I can get an entire matrix of means if I just take a column vector of 1s, that's this guy, it's a column vector because it's just one vector, or sorry, one column, multiply it by this row vector of means. Now I have a matrix of means. Why do I want a matrix of means? Well, because I want to get a matrix of deviation scores. Remember, how did we do this in basic algebra? We calculated deviation scores, and then we squared deviation scores. So now, if I just take my matrix, my original data matrix, and subtract the matrix of means, then my result is a matrix of deviation scores. Now, this is the really cool part, the most important piece. If I take that matrix of deviation scores and pre-multiply it by its own transpose, then what do we get? We get a matrix of sum of squares and sum of cross products. Isn't that cool? I think that's cool. So down here, this matrix is the sum of squares and the sum of cross products. The sum of squares are in the diagonal, and the sum of cross products are in the off diagonal. Now, why is that? Well, what's in the diagonal? Let's go to row 1, column 1. I would go across row 1, down column 1. What I'm doing is taking each deviation score, multiplying it by itself. That's the deviation score squared, and then summing them all, right? That's sum of squares. Pretty cool, huh? How do I get sum of cross products? Well, it's just by doing x and y, same thing. So this is a really nice trick and a fundamental piece of statistics that matrix algebra, there are some special matrices that correspond to really conceptually important pieces of basic stats and multiple regression. So now I think you see we're near the finish line. We have the sums of squares and the sums of cross products. So now if we just divide by n, again I'm doing matrix algebra notation, so we'll multiply times n to the negative 1. Then I get a variance-covariance matrix. And I could standardize that by multiplying by the standard deviation matrix. And if I do that, then I finish with the correlation matrix. So that last piece was just to standardize things so that I get a diagonal of 1s, because each variable correlated with itself is 1. And then in the off diagonals, again, this is a symmetrical matrix. So the correlation between the first column and second column is negative 0.19, and between the first column and third column is negative 0.09, and second and third column is 0.44. So that's the correlation matrix. So again, important things to take away. This is really just purely a mathematical lesson so that we can move on to the next segment and learn how to interpret the regression coefficients, know how to add, subtract, multiply matrices, and recognize that there's some sort of special matrices in matrix algebra that correspond directly to really important concepts in basic stats, like the correlation matrix, sum of squares, sum of cross products, and variance-covariance matrix.